very good afternoon, and today we are going to discuss our topic titled Stokes Theorem in Magnetic Field. So this is the topic belonging to the subject electromagnetic field theory. Already we have gone through several of the live sessions to conduct the solutions for whatever the doubts you have for this particular subject. So Stokes theorem is really very important, and electromagnetic field, as we can classify in the two parts, that one is for the electric and the next one for the magnetic field here. So the magnetic field we have been started with the understanding right from the Biot-Savart's law, and then in the previous session we have also addressed the problems associated to that of the Ampere circuital law. So now the Ampere circuital law application here we extend, and with the help of the two types of the integrals for the same kind of the vector quantity, here we are having the topic the Stokes theorem in magnetic field. So very first of all we shall see what exactly the information is conveyed with the help of this Stokes theorem, and that is of course for the quantity belonging to the magnetic field here. So here we see the illustration. So in this illustration we have one direction denoted by the unit vector small a suffix capital N here. So capital N is basically the representation of the normal direction. So here normal means perpendicular. So whatever the curvature you are having for the surface in this particular illustration, this unit vector at the point is normal to it, it is perpendicular to it. And now to the point of intersection where we have shown this vector that is crossing this surface in the perpendicular direction, we have a small closed loop here. So now you see the loop is of the square shape here, the sides here you see, and this is what the direction to complete this particular loop. You start from any of the corner, you will get back to the same position. So hence this way we can have the closed loop integration for the surface under consideration, and what it yields. So see, this illustration is basically explaining the thing that we have already learned into the Ampere circuital law, and from that knowledge here the Stokes theorem can be simply stated in the term of the mathematical equation here, that we see on the left hand side closed line integral h bar dot of dl bar you can call, that is equivalent to the surface integral of the del bar cross of h bar having dot multiplication to that of the ds bar. So now I will make you familiarize with each and every term in this particular representation, mathematical representation. So here capital H in bold casing if it is there, or while you are writing it manually with your hand, so you can also write it to be H bar here. So this H is representing the magnetic field intensity here. Now the magnetic field intensity vector we are integrating over a line, and that too a closed path here. That is why here on the left hand side we are showing closed line integral h bar dot of dl. So as per the information we have from the Ampere circuital law, it is giving us the net amount of the current flowing, that is inside through that of the closed loop here. So this is what the same. So on the left hand side also you are having the information regarding the total amount of the current that you can denote it by I, and on the RHS also this is of course again I here. As you see del bar cross of h bar here. So with this del operator, which is a vector special differential operator, the cross operation with a certain vector denotes its curl operation. The curl we have already learned so far. So this is nothing but the rotation of a vector, and that is with respect to the area that has it traced thereupon. So the rotation or circulation of the vector that you see here. For the magnetic field intensity, if you try to trace out its rotation, it is giving us to the capital J here. So capital J is nothing but the cross sectional current density. So when you have a conductor like this, and through this conductor if you are having a flow of current here, so wherever you try to take the cross section and how much amount of current is flowing divided by the area of the cross section, you will get this particular vector J here, that also we have learned in the previous session here. So it is cross sectional current density that is usually expressed in terms of amperes per meter square here. So J is nothing but del bar cross of H bar here. So when the cross sectional current density is integrated over the dimensions of the surface, so it will give you the net amount of the current here in terms of the amperes here. The main thing with the Stokes theorem is that on the left hand side as well as on the right hand side, you have the same vector quantity that is represented by here, this time for magnetic field by capital H, representing magnetic field intensity. Same it was the case while we dealt with the divergence theorem. There was also the same kind of the vector both on the left hand side as well as on the right hand side, but the two operations were different thereupon. In the case of the divergence theorem, on one side there it was the surface integral, that it was of course the closed surface integral, and on the right hand side we found the volume integral, the volume integral of the volume charge density denoted by rho v, and here you have the closed surface integral of the d bar, that is the electric flux density. So the same vector we have represented on the LHS as well as on the RHS, and it is of course conveying the same kind of information. So for the divergence theorem it was conveying the total amount of charge enclosed inside the closed surface. So similar is the thing that is conveyed by the Stokes theorem, whereupon the total amount of the current inside the closed loop is conveyed to you people, and that is opposed by the two representations those we have equated in this mathematical expression. So one way is to compute the total amount of current by just having the closed loop integration of the magnetic field intensity vector as shown on the left hand side, and the another way is to carry out first of all the curl operation of the magnetic field intensity vector, or otherwise you may require the value of the cross sectional current density, that it is equal to J bar here. So we have to surface integrate that one for the given dimension, and it will also of course give us the total amount of current flowing through that particular loop here. So this is what the information and the introduction to the Stokes theorem in the magnetic field. Now as a part of practice here, I will try to solve few of the problems. The doubts will of course will get cleared here. So here we go for the first problem statement here. So the first problem statement starts with when x, y and z are positive and less than phi u, a certain magnetic field intensity may be expressed as, it is given by the mathematical expression. Here we have capital H is equal to, in the square bracket we have x square yz divided by y plus 1. This square bracket is multiplied with the ax here. This is further added to thrice x square z square into ay, minus we have the third term as the square bracket having the ratio of x y z square to that of the y plus 1, and it is further multiplied to that of the az here. Now the problem statement continues with the statement find the total current in the ax direction that crosses the strip x is equal to 2, y ranging between positive 1 and 4, z ranging between 3 and 4 also in positive values, by a method utilizing. Here the problem statement is splitted into the two parts. In the part A we have to carry out a surface integral, and in the part B we have to carry out a closed line integral here. So this is what the problem statement given to us, and we have to find the solution for the same here. Now you see here what is the given information in the problem statement. So as we just have the recognition of x, y and z used in this the notation representation of the given vector and everywhere inside, just to provide the or describe the dimensions also here. So this is what consideration of the rectangular coordinate system, where the reference axes are capital X, Y and Z. Those are mutually perpendicular to each other. So this has to be considered X, Y and Z. Now it is considered to have positive directions only, and the ranges are of course less than that of the phi u. Now the magnetic field intensity vector is already given to you, and that is expressed in terms of the x, y and z. So here it is. Now you see this first square bracket in the term on the RHS here, that is multiplied by the AX. So small a suffix x is the unit vector directed towards the positive direction of the x-axis here, and this is what the coefficient. So while you substitute the values of the xyz here, you will get a real value here, that it will be the distance that has been covered by this particular vector from the origin along the positive x direction here. Similar the thing we can see for the second term at the middle, where we have the coefficient described by 3x square z square, and that is multiplied to the ay here. So here ay is the unit vector. This is the unit vector directed along the positive direction of the capital Y axis, whereas here we have the coefficient for the third term, that it is xyz square divided by y plus 1, and this is in multiplication to the az here. Here the negative sign you can take along with this az, that is directed towards the negative side of the z axis. When we are taking it in upright orientation, this is of course the downward direction here. So from the given information, what we have the magnetic field intensity vector expressed in terms of the rectangular coordinate values here. Now we have been provided the information regarding the direction of the total current. See, the total current is directed towards the AX vector, it is unit vector, so along the positive x direction here, and it is also giving us the information regarding the closed loop that is considered on the surface here. The surface is not closed, it is open here. There it is a portion of the plane x is equal to 2. So x is equal to 2, it means it is a plane that it is parallel to that of the yz plane at a distance of x is equal to 2 units on the positive x axis here. Now the y unit and z unit are not limited from minus infinity to plus infinity, they have a range. So y is equal to 1 to 4 and z is equal to 3 to 4. So the situation we shall first of all try to understand with the help of one of the figure that we are going to draw here, and then by utilizing those understandings we are going to follow the methodologies of utilizing the surface integral and the closed line integral to determine the total amount of current in the required direction here. So here first of all we draw the diagram. So for drawing the diagram we will like to take the help of the reference axis from the rectangular coordinate system. Here we take the vertically oriented the reference axis. So upwards you consider the direction of that of the z axis here. So I consider positive z in the upwards and negative z in the downwards here. So you can go from minus infinity downwards, you can go for positive infinity in upwards here. At the middle there it is the 0 value for z, that it is the location of the point origin here. Now this is about the z axis. There it is another axis we are going to draw, that is mutually perpendicular to this one. So here we draw in the horizontal orientation. On the left hand side you consider the negative values of the y axis, whereas on the right hand side we have positive values of the y axis. So this is also naturally ranging from minus infinity values to the positive infinity values. The intersection of the two, at the center you see a point that it is origin here. So it is having the y and z coordinate values to be equal to 0 for both the reference coordinates here. Now there it is, the third mutually perpendicular axis to these one, that it is the x-axis. So this is basically perpendicular to the digital screen that you and I are watching here. And in the 2 dimension, as we have a limitation, we are just drawing it with the help of a tilted line here. But basically this positive x is coming out of the digital screen towards you, and negative x that I am showing on the reverse end here, that is going inside the digital screen in the back direction here. So these are the three reference axes we have considered here. Now getting back to the problem statement, we will have the first of all range of the y values. Y is there in between 1 to 4, and range of the z values, z is there in between 3 to 4 here. Now you just imagine this rectangular shape here. So this rectangular shape, you see this particular edge of this rectangular shape, so this corner or this corner also, they are making y is equal to 1. They are making y is equal to 1. Whereas these two corners, if you see, they are making y is equal to 4 here. Y is equal to 4. Now as we see, these two corners, these 4 corners in total, they are also having the markings onto the z axis. So a pair of the 2 corners, they are having the marking on the z axis at z is equal to 4, whereas these two at the downwards here, they are having z is equal to 3. So whatever the limitation we have shown with the range of the y and z, that is y in the range 1 to 4 and z in the range 3 to 4, we have shown in this particular illustration here. And now you see, this is all we have drawn in the yz plane, that is of course in the positive sides here. So here it is what the quadrant we have on the right hand upper side here. As we like to include the x is equal to 2 here, so you see there we have to draw a plane parallel to this particular dimension, that is at a distance of 2 units along the positive x-axis. So it is coming 2 units outside the digital screen that you see. So here we find here the another screen that it is parallel to the earlier one. So whatever the portion you see that is colored with the yellow color, this is our required surface. So this surface is defined by x is equal to 2, y ranging between 1 to 4 and z ranging between 3 to 4 here. So for this particular surface, we have to also consider a normal direction here. So a normal direction, it means a perpendicular direction here. So either the perpendicular direction will be coming out of the digital screen or going inside. So only the 2 possibilities here we have, and as we are already provided as per the problem statement, it is along the positive x-axis here. So here we show the direction with the help of this particular vector here. So this particular vector, you can also take it to be the small small a suffix x, the unit vector directed along the positive x-axis here. So this is what the understanding of the situation as provided in the problem statement. Along with this illustration here, we are having already given mathematical expression of the magnetic field intensity vector denoted by capital H. Now we are required to find the total current in the positive AX direction. So to determine the total current in the positive AX direction, you have to consider a right hand thumb rule. When you direct your thumb along this particular vector direction here, the curled fingers will be giving us the direction of the integration to be followed for the closed line integral. So here it will be for this particular component that will be along upward direction, here it will be along left direction, here it will be along downwards direction, and here it will be along the right hand side here. So this way on to the given surface here, the circular path, this is not actually circular in shape, it is a closed path in the rectangular shape. So this has to be considered here. And next we can have the utilization of the surface integral and that of the next one here we have the closed line integral here. Now first of all we have a consideration of the surface integral. The surface already I have shown to you with the help of the yellow color here. Now here we need to find that current density first of all to before finding out the total amount of the current here, because we have been provided the vector representation for the magnetic field intensity, and if we find out the curl operation for this given vector here, so that will be nothing but the cross sectional current density expressed in terms of ampere per meter square here. So therefore what we are going to do, since the strip lies parallel to the yz plane, we need only to find out the x component of the current density, and therefore instead of taking the complete formulation to find out the curl of the given vector here, we go with the operation that we denote here by J is equal to the del cross of H here. Now you see del is also a vector. Generally in terms of the rectangular terms, thereupon we have been utilizing it like the representation del x ax added by del y ay added by del z az here. So these are del x del y del z, the partial differentials for the quantity. So these are with respect to x, y and z correspondingly, and these are again along with the unit vectors directed along the x axis, y axis and z axis. So here we are making the use of only the component along the x axis here, and this curl operation can be further expressed as the subtraction of the partial differentials. The first one is del hz divided by del y, and the second one is del hy divided by del z here. So when we find out these two differentials and take a subtraction, it will give us the mathematical expression for the cross sectional current density component along the positive x direction, and when we integrate it onto the given portion of the surface here, so by the surface integration, double integration here, we will be known to the value of the total amount of the current in terms of amperes here. So for that purpose here we are just substituting the z component and the y component of the magnetic field intensity vector denoted by h here. So h initially that I have already from the problem statement, x square yz by y plus 1 ax. So this is hx. We treat 3x square z square in multiplication to ay, this we can treat as hy. So hy can be substituted into the second term on the RHS here. Then we have minus of the square bracket hyz square divided by y plus 1. So this is nothing but the hz component that we can substitute into the first term on the right hand side here, and then we can find out the differentials here. So the substitution of the hz and that of the hy components from the given vector here at these places, and then just finding out the derivatives for the same will lead us to the step where we get the RHS, that is equal to minus of the bracket where we have x z square divided by y plus 1 bracket square. This is added to the second term given by 6x square z, and this is all directed along the ax unit vector here. So now the value of the cross sectional current density along the x component we have obtained, and that is represented here by the jx here by this RHS just now we have find out, and now we need the total amount of the current through the given surface here or the strip here. So for that purpose we shall denote the total amount of current by capital I here, and we can find it out by just having the surface integral j bar dot of ax in multiplication to the differential area dA here. One student here, Survin Mali. Hello sir, if you have any doubt you can ask me, or I can continue with this problem. Yeah, so now the surface integral, it means a double integral here. You can get back to the diagram that I have drawn to you, and thereupon you see the edges of the rectangular surface. One pair of edges is parallel to that of the z-axis, another pair is parallel to that of the y-axis here. So the differential surface we can define by dy and dz, and the dimensions along the y and z axis can be utilized here. The range is already provided in the problem statement that we can utilize here. So here j, as from the above equation, is negation of the bracket here. So we first of all take the negative sign, then the double integrals, here we put the limits. So for z here, there it is the integral from 3 to 4. So the first integral, so the integral from 3 to 4, it is for dz, and the second integral from 1 to 4, this is for dy here, and this is what the bracket that we carry from the above step here, and also putting the value of x is equal to 2, because x is equal to constant here, whereas y and z are varying in this particular range that we have put up on the integral signs here. So this will just have a modified look of the bracket that we carry from the above step here. And now one by one we have to solve this integral, one for the range of y, another for the range of z here. So here we first of all solve the integration along the y dimension here, and we apply the limits here. So now minus of the integral from 3 to 4 for the dz we keep as it is, and we put the limits 1 to 4 to the bracket that we have substituted in place of j here. So it is minus twice z square divided by y plus 1 added by 24 zy. The limits we apply from 1 to 4 here. The application of the limits to this will give us the new step where we have the negation of the integral from 3 to 4 dz, and inside the bracket we will be left with 3 by 5 multiplied to that of the z square added by 72 times that of the z here. Now the integral along the z can also be solved, as we have already solved with that of the y dimension integration here. So here we solve it for, as in both the terms we have the z component, in the first one that it is z square, and in the second that it is simply z here. So this integral will give us to the new form where we have minus of, in the bracket, 1 by 5 z cube added to 36 z square, and the limits here we show outside the bracket from 3 to 4 here. So when we apply the upper and the lower limits to this representation, we will obtain the value of all this computation, that is equal to minus sign as it is, and the value comes out to be 259 here. So as we were computing the total amount of the current that is passing through the surface area that has been discussed so far, so here we can also put out the unit of measurement in SI system of units here, that is in terms of amperes here. So for the part A, utilizing the surface integral methodology, here we are successful to determine the total amount of the current, that is equal to minus 259 amperes here. Now you see that the minus sign here it is just having the representation that the current is flowing in the reverse direction here that it was initially considered. So this has to be a reversal to the consideration of the positive AX direction here as per the given magnetic field intensity vector here. Now we concentrate on to the part B of this problem statement here. In the part B of the problem statement, we have been asked to find out the total amount of current flowing through the system here, where we have to carry out a closed line integral. So just recall back, in the beginning I have already shown you the mathematical expression as per the Stokes theorem here. So on the left hand side we had closed line integral h bar dot of dl bar. So here we will like to express capital I is equal to closed line integral h bar dot of dl bar. Now see here, both the methods are intended to find out the total amount of current, but the ways are different here. Only the methodologies are different, but intention is the same here. So as we are having a closed path here, so from the point where we had started, we have to come back to the same position here, so that the edges of the surface under consideration, the closed loop that I have already shown in the figure here, that we are going to split into 4 parts here. So the first part we will like to start with the value of the y, where y is equal to 1 and we go up to y is equal to 4 there. Then from that particular corner we will go along the z direction here. So from z is equal to 3 units we shall go up to z is equal to 4 units, that will be along the positive direction here in the upwards. And then from y is equal to 1 to y is equal to 4 we shall go, and then from z is equal to 4 to that of z is equal to 3 we will go, and this way we shall complete the closed path of integration here. So that is why the RHS that we have represented in this mathematical equation, we shall split into the 4 parts like this. So here you see, in the first part we have the integral 1 to 4, and simultaneously we also substitute the constant values. Only the thing that is varying here we shall apply along with this limitation here, whereas the other two values will be constant. Obviously x is equal to 2 here, and while we are varying the y component, either the z value will be equal to 3 or that of the 4 here, that we conveniently substitute here and find out the values here. So this is what the second term for the second path, that is a part of the closed path here. This is the third term, and this is what the fourth term here. So in all these particular 4 terms we have either the variation along the y or that along the z here, and those two which are there along the y here, they have the reversal sign here. Here we are going from 1 to 4 in the first part, whereas we are going from 4 to 1, the reverse path here. The same we see here for the dz component here. Here we are going from 3 to 4, here we are going for 4 to 3. So only that thing is there. So that is why drawing diagram while solving the problem keeps it very important to be on the track. So now here we have put up the constant values here. We just need to integrate the things and apply the limits here. So by the next step we have the simplified representation, as for the first term we have 108 multiplied to that of the 3. In the second term we have a negation sign, the ratio 8 by 15 multiplied to 4 cube minus 3 cube, added by 192 multiplied to 1 minus 4, minus 1 by 3 times we have 3 cube minus 4 cube here. So if we calculate all this, that is represented on the right hand side of this expression, this is also giving us the value minus of 259. So this was also the answer for part A. In the part A we had followed the surface integral, and thereupon as per the given details for the given information we found that minus 259 amperes of current is flowing for the concerned path here. So here it is also the same thing here. The one advantage of making the use of Stokes theorem for determination of the various values in the magnetic study or the magnetic analysis, here it is that we are provided the 2 ways. So it is just to tally one another that whether we have made the same correct calculations or not. So this way for both the parts, for part A and part B, we have obtained the answer. The answer you can also outline here. So answer can be simply written capital I by the closed line integral or the surface integral. This is equal to minus 259, and you can provide the SI system of units for the representation here. So this completes our first problem statement, that is based on Stokes theorem in magnetic field here. So after this problem statement, we are going to solve one more problem that will practice a lot here. So here we see another problem statement that starts with, the statement is, the magnetic field intensity is given in a certain region of space as, here again the magnetic field intensity vector is described in terms of the rectangular coordinate values here. So here we have H is equal to x plus 2y divided by z square. This ratio is multiplied by ay. Further it is added to 2 by z in multiplication to az, and this H is expressed in terms of amperes per meter, that it is the SI system of units for the magnetic field intensity. Now what is the exact problem part? The exact problem part is divided into 4 here. In the first, that it is represented by part A, we have to find the curl of the given magnetic field intensity vector H here. So del bar cross of H bar we have to determine. After this we have to find J bar. So J bar is the cross sectional current density, is also to be determined by utilizing the given details from the problem statement. Now based on to the value that can be determined as a solution for the part B here, in the part C it is said that use this value of J to find the total current passing through the surface Z is equal to 4, X ranging between 1 to 2, then Y ranging between 3 to 5 in the AZ direction here. And lastly, in the part D we are asked to show that the same result is obtained using the other side of the Stokes theorem. So this is what the problem statement here we have. Now we have to find the solution to all these 4 parts, as represented by part A, part B, part C and part D here. So as like the previous problem, here we are given the mathematical expression to represent the magnetic field intensity. Sorry. So here we have the magnetic field intensity vector represented by only the 2 components, one component along the positive y direction, hence the unit vector ay it is there, and the another component is along the positive z direction, hence the unit vector az here. These are the coefficient values. So x plus 2y divided by z square can be denoted as capital H suffix y, whereas 2 by z can be denoted as capital H suffix z here. So hx component is equal to 0. Hx component is equal to 0. So for this much of information, we are making the utilization of the general curl expression, that is in the rectangular, also known as the Cartesian coordinate system, and the expression here we have del bar cross of H bar is equal to, the applicable thing it will be minus of the partial differential of Hy with respect to this head multiplied by the Ax unit vector. This is added to the partial differential of Hy by with respect to the x spatial dimension multiplied by the Az here. So in this expression we have to put up the Hy component. Hy component just now we have seen that it is x plus 2y divided by z square, that we substitute here, and the substitution gives us, after finding out the differentiation with respect to z and x, so that it is equal to we have it like 2 in the bracket x plus 2y divided by z cube, and this is further multiplied by ax, and this is further added by 1 upon z square az in terms of amperes per meter here. So this can be the solution for the part A. In the part B we have been asked to find out the J here. So as per the understanding from the Ampere's circuital law, Del bar cross of H bar is nothing but the J bar. So whatever the circulation revolution of the magnetic field intensity vector is there, the same amount of current flows through, and if you have the cross sectional area to find out the density, the J, it will be the same here. So del bar cross of H bar is equal to J. That is why the J can also be the same expression, 2 in the bracket x plus 2y. This is all divided by z cube, and this ratio is multiplied to the Ax unit vector. Further, it is added by 1 upon z square in multiplication to the Az component, and this can be expressed again in terms of ampere per meter square here. So this is what the answers for part A and part B here. Now we require the answer for part C. In the part C, we have been asked to utilize the expression that we find out as a solution to part B for the J here, for finding out the total current passing through the surface, that is defined by Z is equal to 4. So Z is equal to 4 mean what? When we talk about Z is equal to 0, so Z is equal to 0, it means it is a plane that is parallel, or that itself is a plane, xy plane here. And when you have Z is equal to 4, it is parallel to the xy plane, and that has been lifted by 4 units along the positive z axis here. Now generally we have for the xy plane x and y ranging from minus infinity to plus infinity, and this time these have been limited. X is equal to 1 to 2, y is equal to 3 to 5 here. So this way the portion is there, and there should be a judgment of the normal, that is the perpendicular direction to the given surface, and here it is mentioned to be the positive Az direction, that it means in the upwards direction here. For more clarification, I can also draw the diagram. So here you take the horizontal y axis, vertical z axis, and the x axis that is mutually perpendicular to them. So if you have positive x, positive y, I hope you understand the xy plane here. And if you have the markings x is equal to 1, x is equal to 2, then y is equal to 3, y is equal to 5. So this time you can imagine a portion like this from the xy plane, and this you have to lift up by 4 units. So here it will be a portion parallel to the earlier one. So this is nothing but z is equal to 4, x ranging in 1 to 2, y ranging in 3 to 5, and the direction is positive Az here. So for this much of information, we will like to have determination of the total amount of current passing through the surface. So the total amount of current can be denoted by capital I here. So it is expressed by the surface integral of the J vector here. So J vector has to be dot multiplied with the direction, that is Az unit vector here, and the differentials dx dy are a part of the integral representation here. Now here we apply the limits. So here we first of all have the limit for the y value here. So limits 3 to 5 for the integration for the dy, and 1 to 2 for the dx here. So here we see y is equal to 3 to 5 along with dy, the change in y, and x is equal to 1 to 2, the change along x is denoted by dx here, and z is equal to constant, z value is equal to 4. As we substitute in the earlier representation, it will be 1 upon 4 square here. So this is what the thing here we have, and everything it is there constant here, and it is quite simple to find out the integration here. This integration will give us the value of the total amount of the current, that is equal to 1 upon 8 here. Either you write 1 upon 8, or you can also write it to be 0.125 here. So that is of course to be expressed in terms of the amperes here. So this can be the solution to part C of the problem statement here. Now after finding the solution to the part C here, now we require the answer for part D here. In the part D, the question is, show that the same result is obtained using the other side of the Stokes theorem. Now in the part C we have just made use of the surface integral. So surface integral side, it means the expression you recall I showed you in the beginning here. The surface integral I have shown on the right hand side. So the left hand side of the earlier notation for the Stokes theorem we have to utilize here. So that it is of the closed line integral over the magnetic field intensity vector H. So closed line integral H bar dot of dl bar is to be determined, and that is of course onto the square path for the plane represented z is equal to 4. Then we have x ranging 1 to 2 and y ranging 3 to 5 here. So this will be involving the two integrals of the y component over the h over the range 3 to 5 and the integrals over x to complete the loop. So here do not exist since there is no x component of h. That is why here we can express I is equal to the closed line integral h bar dot of dl bar provided z is equal to constant with the value 4 here. So this we can split up into the two parts here, so that it is the integral 3 to 5 dy for 2 plus 2y divided by 16. This is further added to the integral 5 to 3 dy. This is over 1 plus 2y divided by 16 here. So just finding out the integrals here, we shall be left with the new step, that it is 1 by 8 in multiplication to 2 minus we have 1 by 16 in multiplication to 2 here. So this is again giving us the value 1 upon 8, and as this is the total amount of the current, so for the current the SI system of unit is ampere here. So as stated in the problem statement that it was expected to find out or to result into the same value as we have for the preceding section part C here. So the same answer we have obtained 1 by 8, or you can also make it to 0.1250 amperes here. So this way we have found the solution to all the 4 parts of the second problem statement. I hope your doubts have got cleared here. So now in both of the problem statements we have utilized the sides of the Stokes theorem here, and for solving these two problems we have also first of all introduced you people to what information is conveyed by the Stokes theorem here. As far as this particular subject electromagnetic field theory is concerned, generally the syllabus that it is split it into the two sections, section A and section B here. So always and always there it is a possibility that there it is a problem based on to the divergence theorem in section A, and an equivalent kind of the problem for more marks that is expected in the section B for the Stokes theorem here. So practice is a must here. So now after these two problems, as we have the time, we shall go for the third problem statement here. The third problem statement, instead of just following the rectangular coordinate system of representation here, we have the two alternative as well. The cylindrical coordinate system we have learnt in the beginning, there it is spherical coordinate system as well here. So here we will try to have the problem statement that is belonging to the spherical coordinate system of representation. Yes, we have the problem. Now the statement is evaluate both the sides of the Stokes theorem for the field represented capital G is equal to 10 times sine theta into a phi unit vector, and the surface that is defined by r is equal to 3, theta ranges between 0 to 90 degree, phi angle ranges between 0 to 90 degree. The problem statement continues with the statement let the surface have the AR direction, and the Stokes theorem will have yes, of course, by the mathematical expression here we show on the left hand side the closed integral g bar dot of dl bar here. So as this is the closed counter integral here, we can represent in the suffix, we can show it by the c. Either you see you use c for the closed counter integral here, or L for the line integral here. So on the right hand side here we have the representation of the surface integral. So it is double integral del bar cross of g bar is the curl operation, and that has to be having a dot multiplication with the normal direction denoted by the n here, and dA is for the differential surface here. So now you see that a vector is given to us that is denoted by capital G, and the surface it is there. Now in such problems the integration procedure to solve will be a quite lengthy one, and to get that easily done, there it is a requirement of imagination what exact surface, what dimensions we have at our hand here. So to have the r, theta and phi, we have to go back to the details that we have seen for the spherical coordinate system. In the spherical coordinate system, the origin is the reference. So if this is y-axis, this is x-axis, z-axis, x-axis, the three axes I will try to redraw. Here it is the x-axis, and this is the point origin here. Now r is the radius value, so we have to imagine a sphere with the radius is equal to 3. Just consider the symmetry here. Theta is the angle made by the radius segment with that of the positive x direction here. So from the upwards when we are measuring here, so the maximum limit is up to the negative x direction, z direction, that is 180. We have to start at 0, we have to end at 90 degree. So the latter half on the southern side we have to discard. Only the upper half of the sphere, the hemisphere, we have to consider. That too, from the top view we can split up into the 4 parts based on the range of the phi, and that we have to limit to phi is equal to 90 degree from 0. So here we can draw a portion. So this is what the surface. So now you see this bottom edge is having the change along pi. Okay, so generally the practice is to represent it by simply d phi, but it is rho into d phi, whereas rho in the spherical coordinate system is equal to r sin theta d phi. So you write it r sin theta d phi here, and these two edges they are having the changes along the theta direction here. So they are r into d theta, both the surfaces here, and here r is equal to constant, r is equal to 3 here. So this information we can utilize for finding out the corresponding solution here. So I think we shall have first of all the solution for the left hand side, that is the closed counter integral g bar dot of dl bar here. So here we go. This we can express as this is the closed counter integral, the line integral here we have to see. First of all we shall have for the range of the theta and then for the phi here. So here we can denote it as the integral 0 to pi by 2 tan sin theta, whereas we have pi by 2 value into a phi, and this is having the dot multiplication with the another a phi component in multiplication to 3 sin theta, where again theta we put pi by 2 here, d phi here, and this is giving us the value that is equal to 15 times pi here. So this is what the solution for the half portion here, the left hand side, it will be a solution for. Now we have to find out the solution for the right hand side here. So for that purpose what we need to do, the right hand side you see here we have the surface integral for the vector that is obtained after the curl operation of the given vector g here. So g is equal to this much here. So first of all we shall find out what is the curl of this, so that we can substitute in place of this bracket and then carry on the surface integral here. So here we have the curl operation, and the formulation is to be used from the spherical coordinate system. I hope you remember the problem formulas that I have already provided to you in my previous sessions. So here we have del bar cross of G bar expressed in terms of only the AR component we require, only the component along the radial direction of the sphere. So this is 1 upon r sin theta into the differential of the bracket with respect to theta, where the bracket is sin theta in multiplication to 10 times sin theta here. So this differentiation and multiplication to the constant ratio that we have shown in the beginning, this can be nothing but 20 times the cos theta divided by r in multiplication to the unit vector AR here. So this is the simplest expression we can put up in place of the del bar cross of G bar, which is there to be surface integrated in the right hand side of the Stokes theorem mathematical expression here. So here we go. So we put up the surface integral del bar cross of G bar having dot multiplication with the normal direction into the differential area, that is equal to the integral ranging 0 to pi by 2, another integral also ranging 0 to pi by 2, and that is applicable to the 20 times cosine of theta divided by 3 along with the AR dot multiplication with the AR into 3 square sin theta d phi here, and this value will also give us to the solution that it is equal to 15 pi here. So here we are tallying the answer. So here the thing is, we have the solution after evaluating both sides of the Stokes theorem for the given vector field capital G. Both the sides are yielding the same value, that is equal to 15 pi here. So the new thing that it was in this third problem statement, that instead of having the working into the rectangular coordinate system representation, here we had opted the spherical coordinate system of representation. So therefore the integrations were of course along the theta direction change and that of the phi directional change here, and of course the determination of the curl operation. For that purpose, the corresponding formula for the spherical coordinate system is to be utilized here. The formulation in rectangular coordinate system is quite easy to understand, but if you have a clarity how to get conversion of the coordinates from rectangular to cylindrical and cylindrical to spherical here, so you can get it modified into the representation as per the requirement here. So this was our third problem, where again we have dealt with evaluating the answer by utilizing first of all the closed line integral and then by the surface integral along with the determination of the curl operation here. So the three problems we have dealt thereupon. Now let us have one more problem. In this problem again we are going to have a practice utilizing the spherical coordinate system of representation here. We will have the determination of the closed line integral, that is the left hand side of the Stokes theorem representation here for a circular path defined by the spherical coordinates here, and we of course will be having the evaluation of the right hand side for the curl operation integrated over the given surface for whatever the surface that is defined by the spherical coordinate system representation here. So let us start with the problem statement. So the problem statement is, let capital G is equal to 15 times r in multiplication to the a phi unit vector here. Now we have the continuation of the same to have the part A. In the part A we are asked to determine the closed counter integral G bar dot of dl bar for the circular path r is equal to 5, theta is equal to 25 degree and phi is equal to 0 to 2 pi radians here. And in the part B we have been asked to evaluate the surface integral G bar cross of G del bar cross of G bar dot multiplication with the ds bar over the spherical cap r is equal to phi u, theta ranging 0 to 25 degrees, and here we have phi in between 0 to 2 pi radians here. So first of all, with respect to the given information as per the problem statement here, we will try to understand the exact situation with the help of the geometric diagram. Please consider the symmetry while I draw this particular figure. So let us have the consideration of the origin to be the intersection of the three axes. Those are mutually perpendicular, and these axes are of course from the rectangular coordinate system here. So x, y and z axis here. So this is positive x, negative x, negative y, positive y, positive z here, negative z here. So r is equal to 5. So r is equal to 5 in both the situations. So we have to consider a sphere that is centered at the origin, having the radius r is equal to 5 units here. Now theta is the angle that we measure from the upwards direction here. So this radial segment has to make 25 degrees angle with that of the z axis, positive side. So this will be first of all for the first part here, or for the second part also, will be giving us a conical shape apart from the spherical surface here. And see, we have the phi in total range 0 to 2 pi. So basically here we have such a conical path. Its periphery is to be the closed loop for determining the closed line integral g bar dot of dl bar, and it is also to be utilized for the surface, that is a cap here. So this is the surface where we have to find out the surface integral, the curl of g dot multiplication with the ds bar here. So I hope you have imagined the surface that I have shown to you, and now we are ready to find out the answer for. So the first part, you see, determine the closed line integral g bar dot of dl bar for the circular path r is equal to phi u, theta is equal to 25 degree, phi ranging from 0 to 2 pi here. So therefore here we put up the closed line integral g bar dot of dl bar. You see the path is there along the change of the phi angle. So phi is to be taken in the entire range, full range, 0 to 360 degrees if you take, or 0 to 2 pi radians here you take. So that it is the integral 0 to 2 pi d phi, and the integration is on the surface, and that is of course in terms of the r, theta and phi here, and after substitution of the values here we get it to the form. So we write first of all 15r as it is, r is equal to phi u we substitutes. So 15 into phi u into a phi, the given vector g, and the dot multiplication with the dl here. So dl can be described by first of all the direction a phi in multiplication to the r sine theta. So r is equal to phi u, sine theta is equal to 25 degree here. So we get in total 15 into phi u a phi dot multiplied to a phi unit vector phi u sine 25 degree. This is integrated over 0 to 2 pi for the d phi direction here. So here we get it to the simplified form after the integrals to be solved here. So that is equal to 2 pi times 375 multiplied to the sine of 25 degrees here, and this is going to yield the answer as 995.80 here. So this can be the solution for the part A as the answer here. Now we have to go to focus on the part B here. In the part B, you see we have to evaluate the closed surface, not the closed, open surface integral for the curl of G, having the dot multiplication with the differential surface ds here. So first of all we shall have the del bar dot of G bar. that is the curl operation. So again here, for finding out the solution to this curl, we have to make the utilization of the formula in terms of the spherical coordinate system. So in spherical coordinate system, the del bar cross of g bar is given by 1 upon r sin theta. The del theta, the partial differentiation, is applicable to capital G phi component in multiplication to sin theta, and this is all multiplied to the AR unit direction vector here. So just the substitutions and finding out the partial differentials will give us the next step to this, that it is 1 upon r sin theta multiplied to 15r cosine theta AR here. And finally the representation can also be expressed as we have the ratio cosine divided by the sine, so this can be expressed in terms of the cot. So we have 15 as it is, the cosine divided by sine we represent it by cot here. R upon r can be cancelled from the numerator and denominator, so we are left with 15 cot theta AR. So this is the answer for the curl operation here, and then we have to integrate this over the given surface here. Now see, the surface is defined by r is equal to 5, theta is equal to 25 degree, phi ranging from 0 to 2 pi here. So here we represent the surface integral for the curl that just now we have determined over the differential surface here. So the differential surface is to be defined by the two dimensions. So the first dimension for the phi, that is from 0 to 2 pi integral, here we are representing, and the second integral we are representing for the theta dimension, so 0 to 25 degrees for the theta here. So here we put up the curl that we have find out in the next step here, above step here, that it is 15 cot theta AR here. So this has to be a dot multiplication with the differential surface as defined, r square sin theta d theta d phi into AR as the unit vector direction here, perpendicular to the differential surface here. So we find out the dot multiplication and we apply one of the integral that is on the entire range here, and then can put up in the next step that it is 2 pi in multiplication to the integral 0 to 25 degree for d theta applicable to 15 cosine of theta into 25 here. So we shall be left with, after the integral over d theta, 2 pi multiplied to the value 15 in multiplication to again 25 into sine of the angle 25 degrees here. So if you find out the sine 25 degree, multiply it with 25, further multiply it to the 15, further again multiply 2 to the 2 and pi as a constant 3.14 you can substitute, that is equal to the value we are obtaining 995.8 here. Now you see, this is the same answer that we have find in the part A here. On comparison you will find that the second methodology is quite lengthier, because thereupon we have to first of all remember the formulation of the curl operation to the respective system of representation, either rectangular also known by Cartesian, or another is the cylindrical, and then that of the spherical coordinate system, and then the surface integral here. On comparison to it, in only one step, just to have the judgment of the proper closed path here to integrate over the closed path here, the closed counter integral, that will be quite simpler here. Now as we switch from the rectangular coordinate system to that of the cylindrical and cylindrical to that of the spherical here, there are the changes from the spatial dimensions to that of the angular dimensions here. That is why the complexity increases to a little bit here. While we switch from the rectangular to that of the cylindrical coordinate system, one angle is added and one spatial dimension is removed. Whereas while we switch to the spherical coordinate system, as compared to the rectangular one, there are the two angles and only one spatial dimension in the straight direction here. So that is what the change, and the angles bring the complexity here. But if you have the proper concepts and remember the formulation for the concerned operation in any of the system, only three systems you have to study: rectangular, cylindrical, and that of the spherical. You can easily solve these particular problem statements, and you can easily score good marks in the electromagnetic field theory here. So this was our fourth problem statement here. So I hope the understanding of application of the Stokes theorem is quite clear to you people. Now we will like to conclude our lecture just having one more problem, the last problem here. The last problem, again I will be taking on to the spherical coordinate system, because spherical coordinate system is having the two angular terms here, so it becomes quite tedious to always remember. That is why I take one more problem. Just it is having the two parts to be found out here, and then we can conclude our today's lecture here. So here we have the problem statement. Given the expression of magnetic field intensity denoted by capital H, expressed in terms of the spherical coordinates, that is equal to, here we have H is equal to 3r square divided by sine theta a theta added to 54 times r cosine theta a phi in terms of amperes per meter. Then we have the part A to find as a solution. In the part A, we have been asked find the total current in the a theta direction through the conical surface defined by theta is equal to 20 degree, phi ranging between 0 to 2 pi, and r ranging between 0 to 5 units here, by whatever the side of the Stokes theorem here. And then we have the part B, check the result by using the other side of the Stokes theorem here. So this is what the simple problem statement here for working with, for practicing with the problems associated to the Stokes theorem, that is a part of the analysis of the magnetic field here. So always and always I expect the magnetic field intensity vector will be already provided to you, and according to the representation it has, you have to just find out the two integrals, either the closed counter integral or the surface integral along with the curl operation here. It will have a solution for the required things here. So let us find first of all the solution for part A here. So now for part A, we will choose the closed line integral here. So this will be of course h bar dot of dl bar. Now if you recall back to the things where the definition of the surface is there, it is a conical surface. Theta is equal to 20 degree, phi 0 to 2 pi, and r is equal to, we have 0 to 5 here. So here you have a cone, the conical opening, and this opening, every point on this opening is joined to a central point here. Now you see along this particular line we have a change along r. Okay, so we have been defining r is equal to 0 to 5, so r is equal to 0 here, r is equal to 5 here, theta is equal to 20 degree. There it is, the centrally existing axis with which the 20 degree angle is made by every point that is on the surface of this conical shape here, that makes the same 20 degree angle here. So the two things are constant as we are finding the closed line integrals. The closed line integral will be of course onto the periphery of the opening of this particular conical shape here. So one thing is r is equal to 5, and the second thing is theta is equal to 20 degree. Only you have to vary the phi angle, that is from 0 to 2 pi here. So that is why we are expressing h bar dot of dl bar, that is equal to the integral 0 to 2 pi, we have 3r square divided by sine theta into a theta added to 54 times r cosine theta a phi, whereas r is equal to 5 we put, theta is equal to 20 we put, having a dot multiplication to the 5 sine of the angle 20 degree d phi into the minus a phi angle here. Now after this we have to just put the constant values, find out the integration, and that is of course after finding out the dot multiplication here. So this will give the simplification to the right hand side of the mathematical expression, that is equal to minus 2 pi 54 into 25 into cosine of the 20 degree into sine of the 20 degree, and this is giving us the final answer. The final answer here it is minus of 2.73 multiplied to 10 raised to the power 3, and this can be expressed in terms of the amperes here. See, only magnitude we have written here. So this is the result, that means there is a component of the current that enters the cone surface in the negative a theta direction, to which is associated the component of the H in the positive a phi direction. So this can be the solution to the part A, and last we have to find out the answer for part B. The part B is to check the result by using the other side of the Stokes theorem. So the other side of the Stokes theorem, what we need to do, we have to find first of all the curl of the given vector H. So H is there in spherical coordinates. So curl of H is equal to, here we write the general formula in terms of the spherical coordinates, that it is 1 upon r sin theta del theta of 15 times r cosine theta sin theta into ar minus of 1 upon r del r 54 r square cosine theta into a theta added by 1 upon r del r 3 r cube divided by sin theta into a phi here. So this curl operation del bar cross of h bar is nothing but the cross sectional current density, that can also be written as J also. So this gives us J is equal to, we have 54 times cot theta AR minus 108 times cosine theta A theta added to 9R divided by sin theta A phi here. So J we have here, and the second side of the Stokes theorem, we have to just surface integrate this vector J, or the representation as curl of the H here. So here we make the surface integral del bar dot of H bar, del bar cross of H bar dot multiplication with the ds here. So we apply the integral limits to both the dimensions 0 to 2 pi, then the second integral 0 to 5. We have 54 cot theta AR minus 108 cos theta A theta plus 9R by sin theta A phi here. Here the constant theta is equal to 20 degree, we can substitute. Dot multiplication with A theta angle unit vector along with R sin 20 degree dr d phi here. So by the next step we can have the simplification too. After putting the dot multiplication and the theta values, we are left with minus 0 to 2 pi integral 0 to 5 108 times cosine 20 degree sin 20 degree r dr d phi. By the next time after solving the integrals, we are having minus 2 pi 54 into 25 into cosine of 20 degree into sine of 20 degree, and lastly we get it to the value minus 2.73 into 10 raised to power 3 expressed in terms of amperes. So this is the same result that we have obtained as the solution for part A here. So for both the procedures we have got the same result. That is why the objective that it was set there is completed here, that we have cross verified the result by both of the sides of the Stokes theorem here. So this was all about the Stokes theorem understanding associated to the analysis of the magnetic field here. Obviously the vector is magnetic field intensity here, and based on to the same concept we have practiced here the 5 problems. Especially we have first of all dealt with the understanding started at the rectangular coordinate representation, and then directly switch to that of the spherical coordinate system representation. If any of the problem comes in the representation of the cylindrical coordinate system, I am sure that you will certainly solve it uh, with easier. So I hope the things were really very clear to you people. We shall meet by the next week with another topic from the same subject, electromagnetic field theory. Thank you.